All right, we'll get started. Welcome, everyone. So as I said, today I wanted to spend some time looking at some of these sort of more challenging problems that I posted. And once again, these are not being collected. You don't need to turn these in or anything like that, but they're very good to get a better sense of what's going on in the class. So these are the challenge problems that we looked at before, or that we posted to the website. So here's the first one. The first of these challenge problems basically involved. Actually, before I do that, I just wanted to say as an aside, because I got a question. I'm actually gonna do this in a little bit, but I got a question via email, and the question I got via email was when are two vectors parallel? Well, when they're orthogonal, we say we know that V and U are two vectors, are orthogonal. That happens precisely when their dot product is 0. Also, by the way, I apologize because of the dishwasher that's going on in the background. That process was started sort of absent-mindedly before the recording started, so I apologize that there's this little machine going on in the background as I'm doing this. So so when are two vectors parallel? Well, that's when they're orthogonal. And a common misconception, a common error that people often make, and do not let this be you, is it is not the case that if you have that U and V are parallel, which is usually written with this double bar notation, then it does not necessarily mean that their dot product is 1. I don't really know where this comes from, but a lot of people make this mistake. So if they're parallel, then that does not mean that the dot product is 1. It doesn't really tell you anything about their dot product at all, except that it's not 0. The way to identify if vectors are parallel, here's the real trick. V and U are parallel if and only if V is some scalar multiple of U. In other words, if you have that V is, I don't know, A, B, C, I can't use C because I already used C. I'm going to use different letters. I'm going to say V is equal to V1, comma, V2, comma, V3. Then if they're parallel, that means that U is going to be CV1, CV2, and CV3. So for example, you can take, I'll make something up. You can have V as the vector 2, 4, -8, and U might be the vector, I don't know, I'll make something else up. We'll say, for example, that it's -3, comma, -6, and 12. Well, the question is, are these vectors scalar multiples? Are these guys parallel? And yes, they are. You notice, for example, that V is equal to 2 times the vector 1, 2, -4. And U is equal to -3 times the vector 1, 2, -4. So, in fact, what we get from this is that V is equal to U times -3/2. So, or rather, -2/3. Right? And what that means in particular is that U and V are parallel. So that's how you know. A good way of doing that is just factoring out common terms and seeing what's left over. And if what's left over is the same thing, then you can be pretty certain that these vectors are in fact parallel. So if there are no questions about that, I wanted to go on to some of the problems that we're doing today. So I'll make a new slide. So problem 1, these are the challenge problems. And, excuse me, sorry. So the first of these problems is we want to find a sphere of the largest radius and it's centered. It's centered at the point 5, 4, and 9, and contained in the first octant. And what does first octant mean? First octant means that we have that x, y, and z all have to be positive, right? We're saying that that all points x, y, and z with all being positive. So the image we should have in our mind with this, we've got our admittedly fairly rough three-dimensional coordinate system, and we've got our point. Maybe this is I don't know. Maybe this could be our point. So maybe this is our point that we're interested in. This is 5, 4, 9, and we want a sphere that is centered around this point but stays within this octant and doesn't edge out. And now that I've drawn this, we can probably see what's going on. What's the general formula for a sphere? The general formula for a sphere is going to look something like this. It's x minus minus the center. The x coordinate of the center is 5. We know that, squared, plus y minus 4 squared plus z minus 9 squared. And that's going to be some radius r squared. I don't know what that radius is, but I do know that it has to be just large enough that that sphere stays inside of the octant. And if we stare at this for a second, we can probably see what that radius has to be, right? It's whichever of these coordinates is smallest. In this case, the smallest coordinate is the y-coordinate, right? If you go a little bit beyond that coordinate, then you end up creeping out of the octant. You end up going past that plane, and that ain't no good. So it's going to be the smallest coordinate, which is the y-coordinate. So in this case, we know that the radius must be 4. Now, that does not mean that we're substituting this whole thing equals 4. That is not the case. It is 4 squared, or 16. So the final answer is going to be x minus 5 squared plus y minus 4 squared plus z minus 9 squared equals 16. And that's the formula for the circle, or for the sphere. Once again, I want to sort of re-emphasize something that I mentioned before, which is that this class, this is not like most math classes that you've probably taken before. It's very geometric, and a lot of what we're doing here is going to rely very heavily on having some visual intuition of whatever is going on in the class. So we're starting off simple. Before we even get into any of the calculus stuff, we're starting off simple just to make sure that we can actually sort of see what's really going on here. Questions so far? Okay. Here's the second problem. The second problem involves the curve. And the curve that we're given is y equals 2 sine x. We're going to do some calculus here. And we want to know, find the unit vectors that are tangent to, so we're going to find the ones that are tangent, and also orthogonal to the curve at the point pi over 6, comma, 1. Let's see if we can get a sense of what this looks like. So it's a very, 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 very good idea to draw pictures. Even if they're rough pictures, that's okay. It's a very good idea to try to draw a picture of your scenario. In this case, what is our scenario? Well, we have to work with the curve y equals 2 sine x. That's going to look something like this, right? Again, it's a rough picture. I'm not a very good artist, but it's the thought that counts. Now, we have this figure here, and what we're interested in is this point, and this is obviously not to scale, but work with me, pi over 6, 1, right? So we want to know what's going on at that point. Now, we're interested in unit vectors that are tangent and orthogonal to that point. So let's look at what's tangent. The tangent vectors are going to look something like this, right? We know that the vectors that are tangent to that curve are, look something like this. And if we extend this onward, hopefully this looks like a bit of a familiar picture, right? That's the tangent line. That's the tangent line to that curve, the tangent line that we looked at in Calc 1. So what we're actually interested in here in this case is that the tangent vectors, so if we're looking at the tangent vectors, they're going to be in blue. So the vectors that are tangent incidentally, they happen to be parallel to the tangent line. At the point pi over 6, 1. Now, I don't actually need to know what the formula of that tangent line is. If all I'm interested in is the fact that they're parallel, I don't actually care about where that tangent line intersects the y-axis. I care about the direction that the line is going in, right? The only thing that's really important for me is what is the direction that the line is going in. And the direction, right? So you care about the direction of the line, but i.e., what we're really talking about is the slope. What we want is the slope of that line. And how do you find the slope of that line? Maybe someone who's tuned in can type it in the chat box. Maybe think about what it's going to take to find the slope of that line. Anyone figure that out? What we need to do? Well, what we're going to do is we're going to take the derivative, right? The slope is equal to the derivative at the value x equals pi over 6. Well, that slope, we can work that out. That's going to be, so we know in that case that dy dx, just take the derivative as usual, to cosine x, right? But what that means is that The slope is going to be pi over is going to be 2 pi is going to be cosine, or sorry, 2 cosine of pi over 6, and that's going to be 2 times root 3 over 2, or root 3. By the way, you're not going to need calculators for anything that we do in this class, but we are expecting you to know your trigonometry. So if you're rusty on your trig, then now is a good time to begin brushing up on that. So the slope is root 3. Now, that tells us in particular, now what is slope? Slope, as we know, is rise over run. So what that tells us in particular is that for this curve, we can think of the run as being 1 and the rise as being root 3. Right? But in terms of vectors, oh, well, now we know what that vector is. That vector, the vector is going to be root 3, comma, 1. Now, here's the thing. That's not a unit vector, right? We were asked to find a unit vector, and that's not a unit vector. So you might say, well, okay, but that's just a vector, but it's not a unit vector. No, true enough. I'm not claiming that it is a unit vector, but I think making it a unit vector is very easy at this point, because all we need to do is, because that vector 3, or root 3, 1, that, I don't know, that might be this, I'll make it pink. That might be this vector, right? Maybe over here we have root, oh, sorry, I did it backwards. Not root 3, 1, 1 root 3. So let me fix that. I did that backwards. Vector is 1 comma root 3. So this vector, in other words, is 1 comma root 3. But it's not a unit vector, and making it a unit vector is really quite simple. All we have to do is divide it by its magnitude. So to make it a unit vector, all I have to do is divide it by its magnitude, and its magnitude in this case is going to be 2, right? So 1 plus 3, right? 1 plus root 3 squared, so 1 plus 3 is 4. Square root of that is 2. So the unit vector is 1/2 1 comma root 3. Strictly speaking, we need a plus and minus in front of there, because you could be going in the backwards direction also. So we've got 2 different vectors, 2 different tangent unit vectors, one going forward and one going backward along that curve. Now, for the orthogonal vectors, I'll do this one in purple. For the orthogonal vectors, the story is pretty much the same thing. What do you know about orthogonal vectors? Orthogonal, we already mentioned this, right? That means that the dot product is 0. So we want, in other words, vectors A, B, dotted with 1 root 3 to be, in other words, A plus B root 3 to be 0. That's what we want. Okay, well, that's quite easy. Just take, again, plus minus 1/2 times negative root 3 comma 1, right? That dot product will be negative root 3 plus root 3. And that's going to be 0. And then you scale it. So in this case, we've got our orthogonal vectors as well of the negative reciprocal slope on opposite ends of that curve. You see what we're doing here? What we're doing here is we're just finding a vector whose dot product with the tangent vector is 0. That's all that we're doing. And this will work if we take a to be negative root 3 and b to be 1. Now, how do I know that? There are lots of numbers a and b for which that will work. Yeah, that's true. But they're all going to lead us with vectors that are parallel to those two unit vectors in purple that I just drew, the 1/2 plus or minus 1/2 times negative root 3, comma, 1. Okay? And I want to, now, here's a problem that we're going to look at eventually. So, and when I say eventually, I mean next week. So a future problem is, suppose we take a point in three-dimensional space, and we take some plane that, that does not contain the point. And so here's a future problem. So here's our plane, right? It looks something like this. This is a plane in R3, and you've got some point, which I'm going to call P. Right? And maybe it's not a flat plane, but I'm just drawing three-dimensional axis to emphasize that this is, in fact, a plane in R3. The question that I want to ask, though, that we will be asking next week, is what's the distance from that point to the plane? What, in other words, is that distance? Now, we don't have the tools at this point in the semester to answer that question, so we're not going to really go there quite yet. But what we are going to do is we're going to tackle some simpler versions of this to try to get a better sense of how we might eventually go about doing this. So here's a simpler version first. The simpler version first is problem 3 in these challenge problems, which says you've got a line that's given by ax plus by plus c is equal to 0. And you've got a point, which I'm going to call p is x1, y1. And it's not on the plane. Right? It's a point that's not on the plane. So what's our scenario? Our scenario is something like this. We've got a line in two-dimensional space, and you've got a point P, x1, comma, y1. That's not on that line. Oh, line, not plane. Not on line. Oops. Aha. But the same question. I've got the same question. The same question in this case is, what is the distance? And by which specifically I mean, what's the distance from the point to the line, right? I want to know about that distance in particular. And I'm going to call it d for distance. Now the claim is that that distance is given by ax1, x1 is the x-coordinate of this point, plus by1 plus c, a, b, and c are the coefficients of the line equation, divided by the square root of a squared plus b squared. Why is that true? Why is that the formula for that particular distance? Well, let's look at that for a second. Where does that come from? So why is that the case? Well, let's start unpacking this, and we notice that we get ax plus by plus c is equal to 0, and what that also means is that y is equal to negative a over b x minus c over b, if you want to write this in point-slope form. In particular, what I'm saying here is that the slope, or in other words, the rise over run, is negative a over b. So in other words, in this case, the slope vector that we're interested in goes up by negative a and over by b. Now it could have that that these are negative. If one of them is negative, then that just means that the line is sloped negatively. That's okay. That's fine for our purposes. The point is, what that means is that, and what that really tells us is that the vector negative b comma a is parallel to the line, right? But there's something more interesting. The more interesting thing is that the vector AB is orthogonal to the line. And why is that? Well, you take the dot product. You take the dot product and you get AB dotted with negative BA, which just comes out to negative AB plus AB, which is 0. So what am I saying here? What I'm saying here is that we've got another vector, which I'm writing here, which I'm going to call the vector AB. It's the same A and the same B as in our line equation. So that vector is orthogonal to the overall line. Why does that help us? And now here's where things get kind of interesting. Let's take another point. I'm going to call this point Q. Q is going to be x2 comma y2. So let Q, x2, y2, be on the line. And I want to consider the vector. The vector is going to be given by B. The vector B is going to be written as the vector PQ. Or actually, I changed my mind. I'm going to write it as QP. Going from Q. No, I do want it to be PQ. I changed my mind again. And what is PQ? PQ is the vector going from P to Q, right? You know what? No, I'm sorry. I changed my mind a third time. I do want to make it, for illustrative purposes, I do want to make it QP. Going from Q to P. I mean, it doesn't matter. It's going to end up being the same answer either way, but I think illustratively, this is going to be a little bit better. The point is, the distance that we really want, the distance that we're really interested in, is this distance right here, right? That's what we really care about. So let's recap. We've got this figure, just to redraw everything that we just did. You've got, oh, sorry, I want to make these thinner. You've got AB. You've got, and I'm just going to shift over Q a little bit. Just shift it over so that the tail of AB and the tail of QP are meeting. It's fine. That doesn't matter because this angle is still the same. But what we really care about is this distance. And if you've been paying attention and really see what and can focus a little bit on what's been going on with the vector projections, scalar projections, and things like that, we see what that is. That distance, that green thing over there. Let me get a better color, like an orange. That green distance is the scalar component, right? That's the scalar component of QP onto the vector AB. In other words, that's, and you want to be a little bit more specific because it could be in the opposite direction, so we're going to make it absolute value to ensure that's positive. So in other words, that's AB dotted with x2 minus x1, comma, y2 minus y1. You take that dot product over magnitude AB. Now, just to recap, let me just draw the same picture again so that we can all be on the same page. We've got our, I'm going to give it a name. I'm going to call it N. N is going to be AB, and there's a very good reason that I'm choosing the letter N, by the way, and we'll see that next week. So you've got your vector, which is orthogonal to your line, and we've meanwhile got our point Q, we've got our point P, and we've got the vector QP, like so. And we want to find this distance, which I'm saying that that distance right there is the scalar projection comp of QP onto N. Right? And that's the distance that we want. So the distance is, in other words, the magnitude of AB dotted with x2 minus x1, comma, y2 minus y1 over magnitude AB. And that's the same thing as the magnitude of ax2 minus ax1 plus by2 minus by1 over square root of a squared plus b squared. That's starting to look a whole lot like the claim that we had before. But where is that extra c coming from? Well, that c is coming from the fact that that q is this number x2, y2. And since that number's on the line, we have that ax2 plus by2 plus c is equal to 0. So here, ax2 plus by2, actually, that whole thing's going to come out to negative c minus ax1 minus by1 over square root of a squared plus b squared. And of course, that's just the exact same thing that we had before. That's going to be ax1 plus by1 plus c over root a squared plus b squared, because we're dealing with absolute values. So, so multiplying everything inside by -1 is going to change precisely nothing at all. Now, in particular, this problem involved looking at what happens with the number when you have. So let me actually just go to another one over. So, for example, let's take the point P is going to be -2, 3, and the line is going to be 3x minus 4y plus 5 equals 0. If you actually draw that out, it ends up looking something like this. So here are your x and y axes, and you've got the line in question. And the slope, by the way, the slope is going to be 3/4. So in particular, we have 3 -4 is orthogonal. So let's, and we are interested in the point -2, 3, which is going to be somewhere, somewhere over here, right? So that, give or take, is our point P -2, 3. And we have our orthogonal vector, which I have called n in the past. I'm going to continue calling it n now, which is the vector 3, -4, coming from the same 3 and the same -4 from the line equation. Now, by the way, we also know that the point, Q given by, I think that when I did this myself, I chose the point -1, comma 1/2. That's on the line, right? -3 minus 2 plus 5. That is in fact 0. So that gives us this vector, which I'm going to call, which I'm calling QP. QP, in this case, QP is going to come out to -1, 5/2. Right? -2 plus 1, 3 minus 1/2. That's 1, 5/2. And in what that really is giving us here is that this distance, this distance that we're really interested in, this pink distance there, that is going to be, that distance is the magnitude of the scalar component of QP onto the vector n, which in this case is going to be given by magnitude of n dot PQ. If you make it, at this point, if you make it PQ or QP, it really doesn't matter, but well, I guess I'll be consistent with what I just said. QP over magnitude n. And if you do that, what do you get? If you do that, what you're getting is 3 times -1. So in other words, negative absolute value of -3 minus 4 times 5/2. So in other words, minus 10 over magnitude of the over magnitude of n, which in this case 3/4. So that's going to be square root of 9 plus 16. 13 over 5. That's our distance. That's the distance from this point to that line. Now, we have this formula that we just arrived at, right? This ax1 plus by1 plus c, and we can use that too. We can do it, this is a different way of doing the same exact problem. We can instead do this as magnitude of 3 times -2 minus 4 times 3, plus c, in other words, plus 5, over, still we have 9 plus 16 square root. And that still is going to come out to 13 over 5. But I just wanted to point out that you can do this either way, either the algorithmic, sort of straightforward approach, or but I want to emphasize the geometry of what's going on as we're doing all this as well. Right? Also, we were looking at, what was the other one? The other one that we had was, what if you have, this is now in 3 dimensions, you could have you have a line, right? And that line is going to go through the points Q and R in three-dimensional space. And there's a point P that's not on the line. So again, I want to find the distance. Now, in this case, it's not so easy to, now we're in 3 dimensions, so it's not so easy to find a vector that's orthogonal to that line because it's 3 dimensions. There are lots of vectors that are orthogonal to the line, infinitely many, in fact. So what are we going to do instead? Instead, what we're going to do is we're going to look at this QP vector, and we're also going to look at this QR vector. And what's so special there? Well, just to remind us, what are we really interested in? What we're really interested in is this distance, right? But if you expand on that, what that also gives you, you can actually extend you can extend QP to the other side and QR above it, and you end up with this parallelogram. And it turns out that the area of that parallelogram you can write it in 2 ways. You can either write it as, let's say that that's our distance. You can either write it as the distance times the magnitude of QR. Right? The magnitude of QR, which is the standard formula for the area of any kind of parallelogram. But at the same time, we already know in this class that the area of a parallelogram is also given by the magnitude of the cross product. So you can also write this as the magnitude of QP cross QR. Okay, well now it's quite easy. We can see what's going to happen at this point. The distance is just magnitude QP cross QR over magnitude QR. Okay, so we know all that. Now the particular example that we had, which was good to do just so we all remember how to do cross products, involved the points P111, Q068, and the point R is given by -1, 4, 7. Okay, well, PQ, or QP rather, not that it matters really. QP is 0 minus 1 is -1, 6 minus 1 is 5, 8 minus 1 is 7, and QR, -1 minus, so -1. Actually, now that I think about it, I just wrote, is that QP? It's P minus, no, I just wrote PQ, not QP. Let me try that again. I'm sorry about that. I mean, it ends up not mattering because you're taking magnitudes, and magnitudes eliminate negatives, but in the interest of consistency, 1 minus 0 is 1, 1 minus 6 is -5, 1 minus 8 is -7, and QR, meanwhile, -1 minus 0 is -1, 4 minus 6 is -2, 7 minus 8 is -1. And you take the cross product, and what does the cross product become? QP cross QR. I'm just kidding. 1, -5, -7, negative. -1, -2, -1. And what do you get? I is going to be, so it's 5 minus 14. I. J is going to be, so minus -1 minus 7. J. K plus -2 minus 5. Okay. Or in other words, -9I plus 8j minus 7k. Just to double check, 9, so just to check to make sure that we did this correctly, negative 9 minus 40 plus 49 is in fact 0, and we have 9 minus 16 plus 7. And that is also, in fact, 0. What did I just do? I just took the dot product of what I think the cross product is with the vectors that we had before, and it works out. So the magnitude QP, so, good. We're all squared away on that front. So QP cross QR, the magnitude of that is going to be the square root of 81 plus 64 plus 49, or in other words, 80 plus 50 is 130. 130 plus 64 is 194. 194. And so what we can write at this point, we know furthermore that QR, magnitude QR, we can write that QR we know is going to be the square root of 1 plus 4 plus 1, or in other words, square root of 6. Next page. So in other words, QP, so the distance, which we know is QP cross QR over magnitude QR, we just found that that's the square root of 194 over the square root of 6. Find everything out. What does that give us? 194 over 2 is 97, right? Yeah, 97. So it's, in other words, going to be the square root of 97 over the square root of 3. Just seeing if we can clean this up at all. We probably can't. 1/3 root 97 times 3. 7 times 3 is 21. 9 times 3 is 27. 291, I think. So the and that's about the best we can do, but that's okay. That's still pretty good. That's still a nice, it's a closed formula at least for the distance from that line to the plane. And we can keep on doing this. Let's do one more. Well, the last one of these is problem 5 on the challenge problems, which was you've got a plane. Now we're beginning to build up to the problem that I asked in the very beginning. You've got a plane, and the plane it contains the points Q, R, and S, but not the point P. So let's see what this looks like. You have your plane, right? Let's draw a crude plane in what we're imagining to be three-dimensional space. And for strategic purposes, they'll make themselves apparent in a little bit. I'm leaving out a few dashes there. And we have our point P. And we've got our point Q. And we've got our points R and S. R and S are inside of the plane, but P is not. And we want to find the distance from P. I'm actually going to write my R label over a little bit. And we want to find the distance from P to this plane. So how are we going to do that? Well, here's the strategy we're going to use. There are a couple different things we can do. And they basically come out to, the two things we can do basically come out to looking at QP and QS. Let me actually color code those to make it a little bit easier to see, because it's going to get a little bit muddy if I don't start color coding. So QR and QS is going to be in red. And what do we know about QR? So QR cross QS and we can consider that, right? QR cross QS, which I'm going to write up here like so, is orthogonal to the plane, right? In particular, we can imagine sort of bringing the distance that we're really interested in over a little bit, right? So we want this distance, but that's the same distance as this over here, is it not? I think it is. I think those orange distances are the exact same. So we're going to now, for our next trick, we're going to take QP. QP is a vector that's, that's thicker than I wanted it to be. We're going to take QP as a vector that's coming out of the plane up there, and we see kind of where we're getting at. It's the same story from before. So to just expand on this figure, to just bring this over a little bit to see what we've just drawn, what do we have so far? What we have is one vector, which is, I want to make that a little more vertical than that. This is the vector QR cross QS, which for brevity I'm going to call N. And meanwhile, we also have the vector QP, but what do we want? We want to know about this distance down QR cross QS. That's, again, a scalar component. The exact same kind of scalar component that we had before. So, in other words, what is that? That's going to be, so this, no, again, I forgot to make my pen thinner. That, once again, is just the component, the scalar component of QP onto N. That's all it is. And if we unpack what that means that this distance is equal to this scalar component N QP, which is going to be N, or absolute value of N dot QP over magnitude of N. Or in other words, just unwinding everything that we've done so far, that's the same thing as saying QP dotted with QR cross QS over magnitude QR cross QS. All right. So now, at the end of the day, what we're going to do, just to go back way back to what we had before. This is too far. So this is the future problem I mentioned. What it's going to basically boil down to is trying to find some mysterious, or not so mysterious, vector that is orthogonal to that plane. That's where we're going. We're going to find a vector that's orthogonal to that plane and find a way to project a point that we know on the plane onto this vector to get the vector that we really want, this distance vector that we're really interested in. That's what all of this boils down to. But we're not going to do that until next week, when we start talking about equations for lines and planes in three-dimensional space. As an exercise for yourselves, I want you to try doing this with specific points. The points I think that I gave you were P214, Q is 100, R with 020, and S with 0, 0, 3. Try doing that and see what happens. See what falls out after doing it with those values. All right, thank you all very much, and I will see you on Monday. I will be giving the lecture on Monday, and Dr. Roberts will be giving the recitations next week, so we're alternating those. The quiz is available, so you should get started on that, and that's due on Monday at midnight. Good luck, and have a good weekend.